Find the answers to questions you may or may not have asked yourself here at Science, Conversations on Cognitive Science. This episode is hosted by Elisa, Palme and Sönke, Lülf.
A lot of us have made the experience that computers are superior to our human brain in some aspects. For example, to me, I am not good at doing calculations with large numbers, but computers are very fast at that. But then also we are on the internet and we see like a capture, and all of a sudden we wonder why computers are not able to identify blurred numbers or identify bicycles. And in our new blog on modeling the brain, we want to talk about the differences between the human brain and how we can model them with, for example, computers. And for the first episode, we have invited a guest, and we are very pleased to welcome Professor C Kietzmann from the University of Osnabrück. Welcome.
Hi.
And as always, we play our short get-to-know game at the beginning, where we give our guest 5 sentences and ask them to finish them as spontaneously as they can. Our first sentence is, as a kid, I always wanted to be.
A teacher.
For a specific subject or just teacher?
It was 2 things. I either wanted to become an MD for children medicine or become a teacher for math and sports, I think.
Interesting. Okay, a second sentence. If I was an emoji, I would be.
Ooh, that's a good one. I'm not really good with emojis, to be honest. Probably the hugging face one.
That's cute. Our third sentence is, my favorite thing to do on a day off is.
Tricky thing to ask a professor because we're never really off.
True.
But it's not answering emails, I guarantee. It's probably spend time with my kids.
That sounds good, yeah. Next sentence. Right now, I'm most fascinated by.
In science, I'm most fascinated by neuro AI. So the trend of taking inspiration from neuroscience or the brain science, let's call it, including cognitive science, to improve artificial intelligence. Because I think there's a lot of uncharted territory that we haven't even started to explore. And that's why I'm super fascinated by it.
Yeah. And our last sentence. I know it's time to call it a day when.
No, I don't. That's a big issue.
I think that's a typical academia answer. Okay. Now that we have some more ideas of who you are as a person, we also want to know, well, what you do scientifically, where you started your career, how you've gotten to come to Osnabrück, be a professor here. So can you tell us a bit about that?
Okay, the CV in short is I started out in Osnabrück actually as a cognitive science student. And I specifically chose, so the question was, do I become an MD actually, or do I do this ominous like cognitive science thing? And I chose cognitive science because I like computers as much as I liked like biology and medical stuff. So it was a good combination, and it ended up being a good combination. Did my undergrad and master's in Osnabrück, focusing on neuroscience and AI as my 2 focus groups, focus areas. And then did my PhD with Peter Kühne in Osnabrück and Frank Tong in the US. So Frank Tong was or is a specialist in applying machine learning techniques to neuroimaging. And Peter Kühne at the Institute was really good at psychophysics, eye movements, and EEG or electrophysiological recordings. So it was like a perfect match of having somebody thinking in terms of machine learning and patterns, and on the other hand, having somebody who really knew electrophysiology and biological coding. That was my PhD. Postdoc, I went on to Cambridge to work with Nico Kriegeskorte, who's another sort of famous person in that area of comparing brains and machines. So that was, I think, a perfect fit. I spent 3 years in Cambridge, became then an assistant professor at the Donders. The Donders is a brain research institute, and I was at the AI department of the Donders, which again is this combination of these 2 fields. I worked with Marcel van Gerven there, who's an AI researcher, but who's also interested in neuro AI. And from there, I went on to Yeah, to go back to Osnabrück, actually, took my whole lab at the Donders, and we all moved to Osnabrück. Many of them the first time to Osnabrück. For me, it was returning back. And yeah, like the rest is history. We're doing neuro AI sort of research now. The lab is officially called machine learning, which I think is a proper definition of what we do, but we do this neuro AI stuff in machine learning.
Okay, now we've now heard that you were from the beginning quite interested in the intersection of AI and the brain, which I think already quite nicely connects to cognitive modeling, which we will discuss in more detail now.
Mhm.
Could you maybe explain us what cognitive modeling is in simple terms?
Sure. So in my class, I give this class machine learning for cognitive computational neuroscience, which is exactly about this question. Not only how do we use machine learning to sort of analyze brain data, which is one of the ways in which you can look at this intersection of the two fields. Another way of thinking about it is how can we build models that sort of at an abstract level mirror information processing in the brain, and can we then see models as hypotheses as how the brain might be computing certain functions? And so the idea of modeling is that you try to recreate what you think is happening in the brain in a computational system. And in the process of recreation, you realize all the assumptions you're making that are wrong, all of the things that you need to sort of build things. Because a lot of times when we have theories about brain function, we say, oh yeah, it's probably memory. But you don't ask, how would you actually sit down and implement that? Like, how would that even be implementable? Is it implementable in a brain? That's a first big question, right? You can't have a hypothesis about brain function that's not implementable. And at the same time, often we make a lot of assumptions about some prerequisites that then remain untested. And once you have to build a system, you realize all of these things that you're missing. There's a quote that I really like. There was a debate on X or Twitter back then on what modeling is, and Elizabeth Bonowitz said modeling is finally cooking that meal you were certain you knew the exact recipe to, and discovering that it needs salt and somehow the noodles are missing. And I think that sort of encapsulates that whole point. Or to quote Richard Feynman, he had this on his whiteboard in the top left corner, so he wouldn't forget. There's this quote up there where he says, "What I cannot create, I do not understand." And I think this very much encapsulates the idea of modeling, that you make some level of abstraction. You're not trying to simulate the system. You're trying to model it at a more abstract level. And at that level, it becomes tractable, computationally tractable, and feasible to train. And then, sort of, a model is then an instantiation of a hypothesis. And so then you need to contrast multiple models to see which hypothesis is correct.
And for cognitive models, this means that kind of you're trying to model cognitive processes or brain processes.
It depends, right? So your model could be on perceptual decision making, and then many people use drift diffusion models, which are fairly simple, right? They have a handful of parameters of how you think, evidence is accumulated over time and how you make decisions. In the case of what we do in my lab, it is models that have specific features. To me, so we work on visual processing, right? So we wonder, how does the brain extract knowledge from the retinal input that sort of comes in as information. And so what we would like to have as models is that they're image computable, or we call it sensory grounded. So they should be able to take some image that I show people, let's say in the scanner or in a psychophysics experiment, and I would like to be able to show the same images to the model. That already rules out a whole large, if you want natural stimuli, that already rules out a whole large zoo of models that cannot, like drift diffusion models, for instance, are parametric, that in that they don't typically work off of images, right? You think of evidence in a fairly abstract term, right? What's the evidence for A, or option B? So for us, models need to be sensory grounded. They need to be trainable. So we would like them to do stuff. So we would like to put an image in and have the model behave in a certain way so that we can check whether it behaves the same way to a human or not. And even if you have an image computable model that is behaving like people, it still doesn't guarantee that it uses the same sort of representations, the same sort of algorithm internally. So what we need to do in addition is to sort of look into the model and see, can we find a mapping between the representations in the model and what we observe in the brain, and sort of try and deal with this multiple realizability issue that all models have, in that you never know whether your model is just finding another way of doing it that's not how the brain does it. And so we try to sort of, our models do all of these things, try to do all of these things at once. And that's why we end up on, but we're going to talk about that later, I assume, but that's why we ended up on deep neural networks as a fairly good modeling class for information processing in the brain.
Could you maybe, for people who don't, well, people who are not really familiar with the topics, explain what a deep neural network is, or what it's, what maybe like an analogy is that um, is more intuitive to people who haven't worked with it?
Sure. So in the old day, when I started to work on computer vision, we would sit down and look at a problem and think about what is a good feature that would solve this task. So you would want to classify fruit, right? And you would say, maybe color is a good idea. Maybe how round something is a good idea. And you would sit down, and that was known as feature engineering, right? You would sit down, implement those features in a computer vision system, and then apply a fairly shallow classifier on top. That could be a support vector machine, like some machine learning tool that basically takes this representation, these features that you extract from the image, and decides, is it A or B? Is it an apple or an orange or a banana or whatever? Now, the issue is that we were sort of limited by our creativity, right? We would have to sit down and wonder, what could good features be? Deep neural networks sort of circumvent that issue in the sense that they are a set of feature extractors that we don't have to tune by hand, but we allow machine learning tools to use tools that are known as backpropagation or stochastic gradient descent to sort of, given big data, figure out what features are needed in the first place. So think of it that way. I show an image of a dog, and then the network does some random stuff because it's not trained yet. And I tell it afterwards, no, that wasn't a cow, that's a dog. And then it learns to sort of learn from its mistakes, and it adjusts um, little weight parameters throughout the network so that next time I'm showing that dog, it will more likely give the correct answer. And if you do that with thousands of images over thousands of iterations, you can tune the system in that way to sort of behave the way that you would like it to behave. And the benefit of that is that you don't have to think about the features anymore, but the system figures out the features by this gradient descent approach, which features are the most appropriate, most appropriate in quotes, but which features sort of give you a solution to the problem that you're trying to solve. And so that now your thinking needs to shift to a different level, right? That doesn't mean you don't think anymore, but it means you need to think about what sort of architecture would I would like to use, what data set would I would like to use, what should be the error function that I try to minimize with these updates. But yeah, so that's the big difference, I think, in between deep nets and like older approaches towards machine learning.
In that, there is kind of a hint that we lost maybe an intuition or control over what is really happening in those networks, because first you have like the features and you know exactly what the model is looking for. You don't necessarily understand what the um, final function does, but you know the features the model is looking for. And if you just design a model and it finds its own features, then we don't really understand what is going on. And this is like, I think, is often discussed as like the black box of AI. But you also said that in the brain, it's like a meal. I don't know if that's really what you said, but that we don't really know the recipe for it.
Well,
And so
the
we have,
recipe
yeah, sorry.
No, the recipe analogy was for building a model, right? Where you think you know how to build you think you understand the brain process, and then once you start building it, you realize you really don't, right? There's a lot of stuff that you assumed you knew, and then you don't. But the point is well taken. So I don't like the term black box. For deep nets have full accessibility. We know for every single unit or simulated neuron, if you want, in a deep net, what its exact weight matrix is. We know exactly what the input. So we can access every little feature. We can turn off units. We can, activate them. We can do all of these things. So we have full access to the model, which is very different to the brain, where we don't have that, right? So yes, it is true that it's hard given it's a nonlinear process. You start from an image, but then you have this cascade of nonlinear operations. Every layer of a deep net is extracting more and more complex features, right? And it gets hard very deep in, like after a cascade of nonlinear operations, to know exactly what a unit in a deep net is selected for. And I think that's what bothers people, because you cannot know what exactly the feature is. And this is why we do discover that sometimes deep nets do what's known as shortcut learning. They learn in a way that we didn't think they should, but they do, because there was information in the data set that that the deep nets could use, and we didn't notice in designing the data set. But then there's this shortcut, and if there's a shortcut, if my experience is worth anything, if there's a shortcut, deep nets will take that shortcut. And so sometimes we have to retroactively look into the models and try and figure out what they've learned, right? And that is an issue in a way. But worry not, because first of all, the brain is a cascade of nonlinear operations, right? And if we say that a system that we have full access to, that we trained ourselves, that we can fully take apart, that we can lesion, play with, stimulate, do all these things with, if we say that's too complicated, we can't understand it, why do we even bother trying to understand the brain where we don't have any of that? Right? So I think it is a challenge, but it's a challenge we have to face if we try to understand information processing in the brain. So that's one answer. The second answer is that I am not even that bothered by the fact that I don't know for every individual unit in a deep net what it does. If I know that this is an instantiation, a solution of a system that goes into the idea of normative modeling. So I train a system given a given data set and learning rule to do a given task. If now the resulting features look like the brain, that makes me very happy, right? I can say, okay, maybe I've learned something about the brain. Maybe the brain is also optimized towards this function, right? It's asking the why question that is impossible to ask if you only have a brain, right? Because we can't ethically do these experiments where you raise children in a weird world with VR where none of the physics holds true, or where colors are shifted, or where it's complete darkness, or all these things. So I think we need we need the cascade of nonlinearities to have a system that can do anything, because you can't just linearly take an image and do a meaningful operation on it that is in any way near the behavior of humans, because humans too do nonlinear operations on it. And so it's true that we sometimes don't know what the system is doing, but at a higher level of abstraction, we know fairly well what it's doing. We know what it's trained for, we know what it's trained on, we know how it's trained, and so we do have access to all of these things. So yeah, that's the long answer to the black box argument, which bothers me and doesn't bother me at the same time.
You already said that the brain does nonlinear operations, and the AI models do the same. But how much do we actually know about the brain? And is there, like, for every thing that we know about the brain, in computational abstraction? So, for example, like, if I think um, most models are like feed forward, so they only pass information in one direction, and I could imagine that, like, in the brain there are some feedback loops or something. Is that something that is a problem, or is that at this point like something that we just simplified basically and try to understand what's going on there?
So there's multiple questions here, right? One is, do we know enough about the brain to even have meaningful models of what it does? Right? That's one question. And the other question is are the current models that we use faithful to what we know about the brain? Let's start with the second. They're not, because we know a whole lot about the brain, but at the same time, if we simulated all glorious detail, of all the things we know about the brain, we'll fill our GPUs with, a handful of neurons that are incredibly complex, but, don't are not image computable and behaviorally relevant. So there is something to be said about the approach that we take in using fairly simplistic neuron models, which are mostly scalar products in a nonlinearity, in that by simplifying the neuron model away from biological detail, it allows us to have these models that are very powerful, right? Because we spent the parameters on, multiple layers of, a large number of neurons that can learn things, because they're simple. That doesn't say that it's not interesting to try and implement more biological detail as we go along. For instance, one of the things my lab is doing, you know, day in, day out, is think about recurrence. So think about feedback connections and lateral connections in the brain that we know exist, that we know are incredibly important for our visual perception. But most sort of early computer vision models, convolutional models that we got from engineering, sort of were just a feed forward cascade. And it was this simplistic idea: image in, category level, label out on the other end, and you have this cascade of nonlinear operations. Now we know that recurrence, for instance, so having feedback connections and lateral connections, is computationally very efficient because the brain does not live on a large GPU and you can just add a few more GPUs and expand it. No, we're physically fairly constrained in the head, right? So the skull is sort of the limit. And so the brain is using recurrence as sort of a trick of expanding computations, not in space, but in time. And so by integrating these sort of biological details, admittedly at an abstract level, we can get closer to biology and we can understand what the computational function of these computations might be, right? That's the second bit. Adding biological detail just because we know it exists, I dislike as a scientific approach, because I would like to understand, if I put this biological detail in or not, how does the model differ? How does it behave differently? What computational benefits does this feature give us, right? It could be that the brain has a bunch of things that neurons do that are like the appendix of the brain, the appendix of cognition, right? It's stuff that used to be important, maybe, but it's certainly not anymore. And if we try to model it, we might be modeling all sorts of things that don't really have a function. And the only way of finding out what the function of these details is by starting simple, starting very abstract, and then adding details as we go along and trying to figure out what changes in the system once we add them.
I have a question on, because if we add like a feature and see what changes, that presupposes that if we don't add the feature and maybe restart the training, that we would end up maybe like in the same space, or that like the um, capabilities are the same. Is that something that can be expected, or is like starting two trainings could lead to vastly different outcomes and they maybe find different features even if you use like the same or slightly different data sets?
So one thing that we've published on that people weren't ended in the day not so aware of is that even if you stick to the very same architecture, the very same data set, the very same training procedure, the same sequence of images, even, um, if you just change the random seed of what you start your training on, the internal representations of the model are fairly different. And so that's to be taken into account. That's why we typically don't train one model as an example, but multiple models. And we treat the models as sort of participants in an experiment, right? Multiple participants are also different, but there's some unifying principle that we try to study. And so that's one way of overcoming this. The other thing, and that's I think hidden in your question, is another question, in that, is it even feasible to add individual biological details if there could be interactions among many biological details, and we might have to sort of consider very different learning rules once we add biological detail. And yes, that's an issue. That's something to be taken into account. To me, the currently most productive way of approaching the sort of vision problem that we approach is by using deep nets that follow gradient descent sort of optimization principles. That doesn't say that I'm happy with that. I do think that the brain is doing some form of cascaded credit assignment, because how else would you learn very deep into the, or very early in the visual system, which is far removed from behavior? You need to tell all those early areas what they should be doing differently. So there needs to be some form of credit assignment. But yeah, it is true that we need to consider different learning algorithms in the space of more biologically realistic units as we go forward.
In your explanations, or yeah, in your answers, it became like apparent that you primarily focus on visual attention. Is there any reason why that is? Is that maybe well studied, or is that just where you were like the focus of attention?
I don't know, man. It's hard. I've always been fascinated by vision. So when I did during my undergrad, I went to McGill for a semester abroad. And the thing I did at McGill was all the computer vision classes, all the pattern recognition classes, all of that vision stuff, because I was so fascinated by it, by how we take this incredibly complex world of vision with retinal input that doesn't mirror our perception at all, with the retina warping and all that jazz, and come up with a not only sort of meaningful but stable perception of the world, despite eye movements, despite all the uncertainty that you have, despite the vision not being a perfect mirror of what's out there, but a filter towards our sort of world, our evolutionary niche. So it's just this incredibly complex problem to face. And as we see, as you started saying in the beginning, why are captchas hard? Like, if you look at it as a human, you just think, no, it's simple. It's like, it's these few digits and that's it. But that just tells you that we have an incredibly good system to solve that task. And it only becomes apparent when you look at computer vision systems doing it, because you realize how rubbish they are. And so I've always been fascinated by vision. During my later school years, I worked as a graphic designer. I did web design and stuff, and that already was very vision focused. And so I've always been fascinated by vision. And it turns out we know a whole lot in biology also about visual processing, much more than, for instance, about olfaction and other senses. So it's also the perfect playground to sort of, and we have a lot of data to train models on, right? Which is the other thing. Like, try to find an olfaction data set to train your deep nets on. That's hard. But vision, people take pictures all the time. So it's this beautiful set of an incredibly complex computational process that I would like to understand, being fascinated by vision and having the means of actually modeling parts of it, because we have the data and the approaches. So it's both of these things, I think.
We now talk mainly about like the computational side, and that is very logical if we are talking about like computational modeling. But you also said when you talked about Peter Koenig being a supervisor to your PhD thesis that like the biological measurements are like really important. Is there some, or like how do these measurements like EEG um, educate what you are then doing with computers, or is there even a connection? Because I found it like really fascinating how you said in the beginning that like we can use like AI techniques to analyze the data, and then we can use this data to like improve maybe the AI technique that we're doing. And I found that like a very fascinating self-propelling machine.
Mhm. So there's many things to be said. I don't think anybody who has experience with EEG is happy and says this is the perfect method, right? Also, nobody doing fMRI would say that, and also nobody doing electrophysiology, like single cell electrophysiology, would do that, because there's trade-offs for all those systems, right? EEG gives you high temporal, low spatial resolution. fMRI gives you high spatial, low temporal. Electrophysiology, so single cell electrophysiology, or even array recordings in animal models, give you they give you great spatial accuracy and timing, but the coverage is rubbish, right? You only have a very small view on the brain. So we need all of these things together to sort of make sense of the visual system, because remember, vision is, there's careful estimates that, about half of the brain is directly or indirectly driven by visual input, right? It's a huge part of the brain, multiple different brain regions sort of playing hand in hand to sort of give rise to perception. So there's no one answer as to what measurement technique is correct, and some are very much removed from the actual computations. So in EEG, for instance, we don't look at individual cells, right? We look at thousands and millions of cells firing together, so we even have it visible at the scalp level. One voxel in fMRI is, 500,000 neurons, and that's 2 by 2 by 2 millimeters of cortex. So if you want to study human vision, then you're stuck to this sort of very crude approximation. But the hope is that for perception, not individual neurons are driving your perception, but it's always populations of neurons doing that. And that's why it makes sense to sort of think about it. It's even better if you could do array recordings and you get actual, for instance, we have a new project that we just proposed. Think about, spike timing. And spike timing, you can't get out of a population that has to fire synchronously for you to even see the signal, but you need array recordings for that. And so for that, you have to move to a different model, and try and understand that. That is much closer to the actual computations happening, but then you only see a very, very tiny sort of aspect of vision because you only have that one array, which is super tiny, to look at the brain for. So we try to sort of dance across all of these levels of abstraction if you want to sort of make the best out of our knowledge of the system. And there's no perfect electrophysiological or brain measurement technique, let's say, but there's techniques in modeling in how we can't, so representational similarity analysis, encoding models, and so on. The field has developed quite a few techniques that still allow us to sort of analyze EEG data, as crude as they may be spatially, using deep nets, and try and find a mapping between the processes that are happening in the brain when you record it via EEG and what happens in deep nets. But there's always a sort of leap of faith in between, right? But on the modeling side too, right? Nobody says an individual unit in a deep net is a neuron in the brain. A unit in a deep net could be hundreds of thousands of neurons that do similar stuff, right? And that jointly code for a given feature. So yeah, there is a bit of a leap of faith to compare these two systems, but again, it's the best is what we can do right now, and I think we'll be waiting for a long time to get a technique that does all of it at once, and very likely we'll never have it. And then there's another complication, and that is that if you want to do electrophysiology at the sync and at the array level, where you have to do implants of arrays, you don't do that in people, mostly. You can do some of the recordings in people that have, uncurable epilepsy, Parkinson's patients. You can do, but then the placement of the ECOG arrays or the stimulation electrodes is given by medical rationale, not by what us researchers would like to see, right? And so if you want to study more complex designs, more natural sort of visual input, you might want to study people. And once you want to study people, all of the stuff that's closer to the computation is out of the question. And that's why many people study mice and mouse vision or macaques, because that's the only system where we have a chance of looking at the computations a bit more narrowly. And of course, we need to have the maybe this is not the right time or format, but we have to have this debate about animal models, but it's just impossible to do many of these things in humans. And if you want it, so if you want to find cures to some of the visual problems that people face, there's no way around it, right? One of the projects we're working on is with people in Amsterdam at the Neuroscience Institute in Amsterdam, and they are actively working towards a cure for the blind with microstimulation in early visual cortex in people. But of course, you cannot start developing it in people. You have to start with, like, ethically, you have to start with animal models and then sort of build up a good, way of handling these data, and then go from there. And it's yeah, that as much as I love to work towards these things, as much as I'm bothered about the sort of downside of it, right? We can also talk about the CO2 impact of deep learning, right? Which is another problem that we have to face. And I think every researcher has to sort of make up their mind what, to their conscience, what to their ethical view of the world is the right thing to do, that is most promising to help most people, or to bring science forward. And so we make that choice day in, day out. We try to not run models for the fun of it. We're very careful in what models we run, because we know that it's GPUs, where each GPU takes 800 watts of energy, plus all the cooling, plus everything around in this big building that is hosting our GPUs. And it's just something to be aware of. And I in AI, sometimes it can happen that people just scale. And the same goes for electrophysiologists. And um, I think in modeling, in this sort of neuro AI regime, people are very acutely aware of these limitations on both ends, and try to sort of work around getting solutions that are maybe smaller in scale and reach the same performance, that are energetically more efficient than just running stuff on GPUs, right? Ideally, once we have a good model of the brain, we can run a whole lot of experiments on that model. We don't have to run it on people or animal models in the first place, right? But to get there, there's no way around some of that downsides. But I just want to emphasize that a lot of people in neuro AI, I struggle with the AI engineering side of things, because they scale for the sense of scaling. But I think a lot of people in the neuro AI regime are very acutely aware and try to save some of the parameters to sort of get equally efficient but smaller scale models. That's the whole point of why you look at the brain. Because again, the brain uses what, 18 watts of energy, whereas each of our GPUs takes 700-800 watts, and we use 8 of them at once, right? It's a drastic difference. And so that's, I think, why this sort of research is very worthwhile. So that was a long answer
Sorry.
to not your question, but I thought it was important to sort of raise that point.
Yeah. Something I've been with one part of my brain thinking about since the beginning is that for me it's really hard to imagine how to test things on a computational model, which would later apply on the human brain to estimate how, like, I like, it's totally out of my
Mhm.
comfort zone topics, and I only always hear about fancy things people do, and I hear about projects, but I never really get what is possible, what
Mhm.
people are aiming for. So is the goal of those algorithms or of those approaches to, for example, test one brain surgery or one brain treatment, or is it more figuring out how the brain works, maybe to have a model that can kind of well enough simulate how the brain works to understand things? So,
It's yes and yes.
okay.
So some of the things we do are called digital twin approaches, right? Where we try, at a given level of abstraction, try to model as good as we can what we know about the visual system, so that we can sort of figure out what might be going wrong in people with prosopagnosia, right? People who cannot recognize faces, for instance, right? Or what is the predicted change, if you have a retinal disease, macular degeneration or so, right? Your cortex is fine, it's just your retina is not. So what would be predicted changes to, like, if the cortex gets this sort of deteriorating visual input, what will we predict is a typical development of this disease, cortically speaking, right? Because it's important to know how the cortex responds to sort of to this degenerating retinal code, because we want to know, if we were to replace the retina with something else, could we expect the cortex to sort of pick it up again and just work again, right? And these experiments we just can't run on people, but we can start to sort of try and build systems that run through these sort of cascades. Another thing that we do with Emer in Cambridge, who's on parental leave right now, but what we started doing before she had her child was that we ran deep nets through all the typical sort of tests for semantic dementia, right? Which is a disease where people start, like, they can see just fine, they copy visual information just fine, but they lose the sense of semantics. So at the start they would say, oh, that's my dog, it's a cocker spaniel named, Brad. And, over time, they would at some point say, that's a dog, not realize it's their dog. At some point, they would say it's an animal. And at some point, they go to like, it's a thing, right? And to them, the world, the semantic world, the semantic experience of the world gets narrower and narrower as time progresses. And now the diagnostic tools that we have are very limited, right? There's few patients, and we run sort of what we know mirrors their perceptual issues or semantic perceptual issues. But one thing we did was we tried to mirror the progression of this disease in deep nets, and then we can run millions and millions of other tests on these deep nets to see, is there any other issue that these people might have that we didn't yet figure out because we didn't ask the right questions, right? That would be one of the things we can do. We can do very large scale, sort of millions and millions of hours of experiments on these deep nets, which we can't do on people, to sort of figure out, is there any other thing that we're currently missing, right? So this is one important thing. Another thing is, which I'm fascinated by, is what we can do is we can predict fairly well for individual neurons in the visual system how they would respond to a new stimulus shown to the participant, right? So the idea is you show a few thousand, let's say, images to a person, and you learn, and you show the same 1,000 images to a deep net, and now you learn a mapping for the deep net to be able to predict what individual neurons in that person's brain might respond like to new stimuli. So now you have a way of predicting what the brain response will be like to stimuli these people haven't seen. There's two benefits. First of all, we can try and model how, through disease, the system might change. There's another important element. The second important element is, once we can predict how the brain responds to given stimuli, if you have patients whose retina doesn't work anymore, we can take a camera and transform the camera picture into a prediction of what the brain should respond like if it had seen that image. And we can stimulate the brain in that way and hope that the perception of the people will be the same as it was before, although their retina has gone. So you predict what the brain would respond to if the retina was healthy. And then you stimulate the brain that has lost its retina in a way that we know it would have responded to, and then hope that you can sort of bypass the retina that's broken and still give people the ability to see.
Okay, so people would actually see if that works.
Yeah. That's one of the colleagues we work with in Amsterdam is trying exactly that, right? Can we take deep nets to predict brain pattern responses to new stimuli? And can we sort of mirror the perceptual world in people by putting this deep net in between instead of a retina?
Okay.
But that's super far-fetched, right? For all of that to work, for us to sort of mirror retinal coding in a deep net, like in a little device that you have in your glasses or something, for that to work, we need to understand much better what the computations are in the system, right? What are the computations that are meaningful, right? We're back to the appendix of neural computation. That what are the computations that are important for our perceptual world, right? For our perception of the world. Like, not, we don't have to model all of it. There might be some subset of things we need to model and that we need to stimulate for people to have the same perception, right? But for that, we need all of this research, all of this basic research to sort of understand what we need to do, right? Even if the argument is, even if we had the perfect brain stimulator physically, we still wouldn't know how to run it. because we don't have a good model of what the computations are that are important for the brain in that moment of time with that input to give rise to this perceptual process. And this is just basic research we need to do. And we can do it with electrophysiology, and we can do it with deep nets.
But I think to get the most accurate, you would have to do single cell recordings for each tiny bit of a human brain. So basically, spike the whole brain with tiny needles.
Yeah, yeah, yeah. I mean, yeah, you can think about, yeah. I mean, yes and no. I mean, ideally, yes. But I guess the point that many people raise is that if you get early visual cortex, so the first cortical site where visual information hits your cortex, if we get that right and we sort of inject fake activity patterns that are now not elicited by the retina but by us, then the rest of the brain is perfectly functioning and fine, right? We just need to sort of bypass the retina. We don't have to stimulate the whole brain. We just need to stimulate an early part, and then the brain just does what it does. It can take it from there, and it can even learn to adapt to this newly, slightly different code over time. So we still need a whole bunch of electrodes. We still need them in visual cortex, but we don't need them all the way through. We only need them early visual.
Yeah. But there it makes sense if given another example, given different applications compared to the non-seeing people with a retina, that you know where the issue comes from to then try to fix the issue at that specific part of the brain. If there is a specific part and not a whole network, because usually
Yeah.
it's not only one tiny part of a brain when there's a neurological issue, but whole
Yeah.
networks there.
So with like macular degeneration and these issues of the retina, it's fairly obvious, just the retina. But then with the other disease we've talked about, which is semantic dementia, right? There it is the opposite. It's AIT. It's the anterior part of the inferior temporal lobe that has an atrophy and that starts getting worse and worse and worse. And that's why people see fine. The early visual cortex, all of the visual system up to that point is fine. If you give them an image and you ask them to copy it, they can copy it just fine. It's no problem. But it's their perception of the world that then deteriorates, right? And it's a very different approach to model that part because it's at the very other end of the computational graph, if you want. Right. So it depends on the sort of disease that you're trying to model, right? And to be fair, I love to talk about this because it is what I think the use case of our work is. But then 99.9% of work in my lab is not doing that, right? 99.9% of the work in my lab is trying to figure out how all those pieces even work so we can have a meaningful way of interfacing with them, right? But I don't think we're at that point yet where we can do very, very meaningful interfacing, right? And there's all sorts of technical issues with implants that we can get into at another time because the brain doesn't like very long-term implants, and the quality will deteriorate over time. There's scar tissue forming around them, all that madness. That is not my day to day because I'm a machine learning neuro AI sort of person. But yeah, so that's the AI for neuroscience and AI for medical application sort of side of things. But then, as Sönke said earlier, there's the reverse as well, which we can spend some time on if you like, which is how can insights into neuroscience improve AI? Because that I find also as fascinating, which is the other way
Yeah.
around of that part.
I have one really quick question about the semantic dementia thing. Is that only like for one sensory domain? So is that only impacting vision, or does it also are they having a hard time like recognizing voices?
I don't know. I think the most prominent is vision, and I've only worked with patient data who has visual issues, but then at the same time, AIT and anterior inferior temporal lobe is assumed as a semantic hub where many different sensory modalities sort of link into. So if that theory is correct, then yes, it should also affect other senses.
Okay.
And people will have studied this, but and again, colleagues of mine in Cambridge, Matt Lambon Ralph is like the world expert in this sort of stuff. So I'd have to phone Joker him in to say whether I'm wrong or right.
Um, Earlier, you talked about, or with Elisa, after Elisa's questions about like what would be like an ideal way to measure the brain. Are there also like thoughts about the current limitations of what the computational side of things looks like? So you talked about that we use, or that you use GPUs a lot, but that has become like more of a thing in recent years, with like more developments in GPUs. Are there like any approaches, or is there an outlook at what the future needs, or is like GPUs good enough and we now need to focus on like the algorithms?
Yeah, that's a good question. If I had an answer, so I do think that we can do a whole lot of computation that is meaningful, biologically meaningful on GPUs, despite it being GPUs. Um, there, there's spiking neural networks, there's topographic networks that we study in my lab, recurrent neural networks. All these things you can run meaningfully on GPUs. So I don't think right now GPUs are what is holding us back. I think it is more and better brain data that we need to better understand what is going on. I think it is better theory on the brain side because we're like in neuroscience, we're a data rich and theory poor discipline right now, right? We collect a whole ton of data, but real foundational theories on brain computation are very sparse. It's all very local. And I think we need to do better in terms of like theorizing about what the moving parts are doing and build it into models. But it's again not the hardware that is holding us back in that sense. It's the theoretical neuroscience side of things that is holding us back there. And I hope that we can contribute with modeling to that part. So yeah, I don't think I could be entirely wrong. You could, but I don't think it's the hardware holding us back. I don't think we have to go to neuromorphic computing, for instance, right now, right? I don't think um, we need chips that mirror, neuromorphically on the chip, spiking, for instance. Energetically, that makes a ton of sense, but in terms of understanding what is going on, I don't think we need it right now. There's other aspects that we should visit, and that we are visiting in my lab, which is questions about um, embodiment, right? Like our visual system is not meant to just sit there and classify types of dogs. Our visual system is meant for action, right? It's meant to guide our actions. It's meant to give us the information that we, as highly capable cognitive beings, need to navigate this world and to do the right decisions. But we're sort of ignoring a lot of that bit, right? We're treating the visual system a bit as a brain in a jar, where we're saying, yeah, it does this vision thing, and it could be that the visual system is that encapsulated in the brain. I don't believe it, but so that's part of where I think we should be going. And that very easily becomes a big pain in the neck, because now you have to think robotics or virtual robotics, and then you're in the domain of reinforcement learning, and we have projects on it, and it's super fun. But it's hard. It's really hard. So embodiment is one thing. And another project that we've embarked on is to think more deeply about how the visual system develops over time in children, because children start, with fairly poor vision, so no color, very blurry, and then over months you develop color vision. And then not all colors come in at once, and contrast comes in very slowly. And we started with a postdoc and a PhD student in the lab started modeling that trajectory of how children's visual experience changes over their early years. And it turns out that by doing that, you solve a whole lot of computer vision problems that computer vision systems have if you just show them high res images. And that, I think, is again like a neuro AI sort of thing. Shameless plug for neuro AI, but it's not only mirroring, electrophysiological recordings. It's thinking about the embeddedness of the system, right? How does the system grow up? What's it made for? Like, what is all the other things that it needs to do, right? We need to do very fine hand movements that are sort of informed by vision, right? Who models that in current models of vision, right? We're very early in that regard, right? Yes, we do like in my lab, yes, we do that now, but it's very early days. So, and it's not GPU or not GPU, right? There's a lot of questions that you can ask to come back to your questions. It's a lot of questions that you can ask, which are outside of like for which GPUs are perfectly fine.
Sometime earlier, you mentioned that when you compare how much energy a brain consumes compared to an algorithm or an AI, it's quite a vast difference. Do we know how much energy is needed in training models and using models, and what implication that has, especially when we look at trying to, well, reduce our carbon footprint?
Yeah. So this is probably like it's interesting that you asked this now because it's neuromorphic computing is sort of what I said I'm not doing is sort of trying to answer how can we get very energy efficient chips that don't compute everything all the time like GPUs. But I think one thing that we can talk about is the current energy usage of the current sort of AI solutions, ChatGPT and the like. Um, this is not at inference, but if you think about that, just the energy cost and hardware maintenance cost of training GPT-4 is towards the range of 80 million US dollars. I think, and it's in the US where energy is cheap. So I think it makes clear, and this is an exponential growth, right? If you look in the past years towards now, the number of parameters is exponentially growing. The number of energy used and dollars spent on energy is exponentially growing. Um, it becomes fairly clear that this is not something that is long-term sustainable. At least I don't think it is. I know that Microsoft, Google, and OpenAI have requested their own little nuclear reactors to sort of power AI. We can have a debate on whether that is sustainable in the long run or not. But I do think that there's a real chance here where AI has given us as an answer to a lot of the problems that we had. Scale was sort of the answer. It was scale in model size and scale in data. And it's a, it's astonishing and to a degree as a cognitive scientist annoying how capable these models are when you take simple recipes and you scale them up, right? Like if you had asked me what do you need for like to understand what analogies are and all these high level cognitive tasks, I wouldn't have thought next word prediction would have been the key, right? It's like it's deeply frustrating, and at the same time we realize that well, I wouldn't call it hitting the wall, but we're hitting the limits of where the return on investment is getting less and less and less with more and more scale, to a point where the new GPT is called GPT 4.5, not GPT 5, because it was a bit of an incremental sort of uh, impact. And that's because we took fairly similar, and I need to be careful because there's been a lot of development in deep learning theory and deep learning approaches and code bases, not only hardware and data. I think people don't do the field justice by saying, oh, we're just scaling more data and more compute. No, it's like it's proper new ideas. But I do think that to a large degree, the whole idea of what a unit is, a scalar product and a nonlinearity and so on, these ideas we've just taken, they're very, very old. We've just scaled them and scaled them and scaled them. And it's been good. So far, it's been fairly good, a good idea scaling up because things just started working better. But I think we're coming to a point where we realize we can't keep doing that for CO2 reasons, also for financial reasons, and also just to make headway in understanding cognition, building cognitively able systems. That's not the way. So we need to rethink fundamentally how humans, that's my answer. We need to fundamentally rethink how humans compute and think whether there's some tricks that the brain might be using that we can sort of put onto these systems. And that's not only, going for spikes now. It's this whole physical situatedness of the brain, right? In, a skull that limits you in space, in, you know, the energy consumption that's limited because we can only eat so much in a day, right? There's all these things that we need to consider that might jointly give rise to why the brain is so good at what it is and why we, don't have massive foreheads and, so I don't think we can continue scaling like that. This will sort of the other interesting thing is the amount of data. If you look at the how fast human written text scales on the internet is roughly linear. So each year you get this and this much more. Like true human, like right now we have this weird thing where generative AI is just flooding everything, but true human data is scaling more as linearly, whereas we have an exponential growth in the number of data that deep nets use or language models use to be trained on. And the projection is by 2028, roughly, will hit peak data. The deep nets will have read everything people have written on the internet. And from then on, we can't just scale and use more data. It won't be there. People can't create it fast enough. And so that already tells you as well that we have to rethink because kids growing up becoming, very capable cognizers or adults that do fairly simple very complex cognitive tasks have like nowhere near the sort of data input that these deep nets have, right? And we could say, yeah, but those language models, or deep nets slash language models, those language models are experts in everything and people are not. But I would still argue that people are very much better in terms of data efficiency. And so there's a lot that we can learn from looking at the brain and how we can improve AI.
Thank you for that answer. We are slowly coming to an end, and in your answer, you already like nicely circled back to like human cognition. And our question at the end is always, do you have like a brief explanation of what cognition is and what role does it play in your research?
Okay, so cognition. So it's the question that everybody studying cognitive science is wondering about. Like, what is it, and why is it not communication only? Um, so cognition is, or cognitive science is the science of trying to understand how humans and machines is agnostic to the actual implementation, right? Cognitive science, not brain science. How machines and brains process information and sort of can yield via information processing things like perception, attention, memory, learning, planning, decision making, but also, speaking, thinking, feeling, all these things. How do they arise from very foundational signals being passed in biological and artificial systems? And a good cognitive system will be intelligent. But cognition is much broader than intelligence. If you want, intelligence is a measurement of, you know, how good a cognitive system functions as a whole. But cognition is all these different sub-disciplines as well, which is why I think cognitive science is richer than in research on intelligence. But that's another story.
And if someone has listened to this episode, is there one information or one piece of information they should definitely remember?
I think it's an incredibly exciting time to do this sort of research at the intersection of AI and neuroscience because, only 10 years ago we didn't have anywhere near the technical capability of doing what we're doing now, right? It's not only that we didn't have the ideas, we also didn't have the means. And now we're at a time where we do have incredibly good recordings from the brain and the technical ability of modeling stuff. So it's a fantastic time to get into this space because it's really good fun.
That being said, thank you so much for talking to us today and taking the time.
My
It
pleasure.
was, like, at least for me, it was a whole lot of information and stuff to think about and process.
Good.
And I think both of us really appreciate having you as a guest. Thanks.
Thanks.
You've listened to Kaleidoscience, Conversations on Cognitive Science, hosted by Elisa Palme, Sönke Lülf, and Sophie Kühne. Produced by Clara Kühne, Imogen Hüsing, Elisa Palme, Sönke Lülf, and Sophie Kühne. Produced in collaboration with the Cognitive Science Student Journal. The music was produced by Jan-Luca Schröder. The logo was designed by Annika Richter. Thank you for listening and joining us on our journey through conversations on cognitive science. This podcast is not sponsored and does not give us any financial profit. If you wish to support us, the most effective way is to do so by leaving us an up to 5-star review on your chosen podcast platform and following us on Instagram. You can reach out to us via mail, comment on YouTube, or message us on Instagram. We are always happy to hear your feedback. Thank you again for listening to us and for your interest in science. If you have any questions regarding this episode or any of our other episodes, feel free to reach out. You can reach out to us via Instagram by sending us a direct message at kaleidoscience_pod or write us an email at kaleidopod@us.de. You can find both links to our Instagram and also the email address in our show notes. We do read all your comments and will also reply to you as soon as we can.